So good morning, everyone. So my name is Yuri Timrov. I'm from EPFL in Lausanne. Sorry for this technical issue. So welcome to this morning session. Before we go to the lecture, a small announcement. This afternoon, we will make a group photo just before the coffee break. And tonight we have also social dinner. And that's it. So we're a bit running late. It's okay. So we start coffee break also a bit late. And with this, okay, I would like to, it's my really great pleasure to introduce Professor Paolo Giannozzi from University of Udine. And the talk will be about density functional perturbation theory and application to Phonons.
What's happening here? Okay. Okay, good morning to everybody. Sorry for the delay. I'm going to introduce density functional perturbation theory with a special reference to Phonon calculation. I see there are people in the audience that don't need an introduction, I guess, but thank you for coming anyway. Okay, does it work? No. Why? It was working, it doesn't any longer, no problem. Okay. So let me skip the first part, the reminder of the density functional theory. I assume that you are able to compute the ground state of a system. Typically, since we are working, at least in this tutorial, we are working with a plane wave pseudopotential. We are in a framework of plane wave pseudopotential framework. So we have some periodicity. We have crystals in mind. And we have to solve, we know how to solve those Kohn-Sham, self-consistent Kohn-Sham equations and compute suitable form of the density of the functional that defines the effective potential used in the Kohn-Sham equations. So what happens if we perturb in some way our potential? So we have the bare potential acting on electrons, the V, our potential that I've called V in the previous slides. And we make it dependent upon one parameter, which may be typically an atomic position or an electric field or something else. There are many applications, many possible applications for density functional perturbation theory. It works for many interesting perturbations, and let's expand around the zero value of the parameter, with zero meaning lambda equals zero, meaning unperturbed case. We write an expansion like this, first and second order. And we want to know what happens to the charge density, which will also be expanded into first and second and fourth order terms, and to especially to the energy function, to the DFT energy. Where all those derivatives are computed around the equilibrium position, at the equilibrium state, lambda equals zero. So that's the problem that we want to solve with density functional perturbation theory. Now, the first order term is it's quite straightforward, actually. It's nothing but the extension of the Hellman-Feynman theorem to density functional theory. So if you look at to perform explicitly the derivative with respect to this external parameter of the energy functional, you find that there is an explicit term, explicit dependency that I have indicated here, as this term, plus something else, which is an implicit term coming from the variation, the first order variation, first order derivative of the charge density. But we know that the energy functional is minimized by the ground state energy, the ground state charge density. So that term vanishes exactly. Well, exactly if the solution, if the DFT solution is exact. Approximately, if it is not, it's a rather technical problem. But anyway, with plane waves, if the set consistency is good, this term vanishes to a very good degree. So this simply is often referred to as simply a Hellman-Feynman theorem, also for DFT, and it's what is used to compute forces acting on atoms. So forces, if lambda is an atomic position, is the position of an atom in the system. But of course, forces are minus that quantity, minus the derivative. In general, one can show that if you have, so you see that this term doesn't contain any derivative of the charge density with respect to lambda, which is the quantity that is difficult to compute, the quantity that you don't know and you have to compute. In general, one can show what is called the 2n+1 theorem, which is known from quantum mechanics, but which can be generalized to DFT. That is that order n in the derivative of the charge density determines the energy up to order 2n+1. Okay, but this doesn't yet tell us how to find the second order derivative, because second order derivative of the energy, we need the first order derivative of the charge density. So we need the charge response. It is called the linear charge response. Again, using the previous results, one can show that the second order term of the second order derivative of the energy contains a term like this, that is an explicit term containing the second derivative, explicit second derivative of the potential, plus the term that contains, that depends upon the linear response of the charge density. And this is the difficult term. Notice that in general, you may have more than one variable, more than one parameter lambda, a set of parameters, and so you may be interested in mixed derivatives. And so this expression for the second order derivative of the energy can be extended to several parameters, to mixed derivatives. In this way, something that is not obvious, but it's true, it has to be true necessarily, is that this object is invariant with respect to exchange of the two parameters. So this is all obvious here. It's much less obvious here. So the derivative with respect to lambda of this and the derivative of the respect to mu of this don't look really the same as if you exchange the two parameters, but they are. Now, this still doesn't answer the question, how do we find the linear response? Now, one way to find the linear response is to go back to what we have written here, and to write down explicitly this function. And this we know doesn't depend upon the first order derivative of the charge density. This will actually, if you expand, to do the expansion by putting this and this inside this, you write the expansion explicitly, you find the functional of the linear response. Actually, it's a quadratic functional. find the quadratic function of this quantity, the quantity you need, and if you minimize this quadratic functional with respect to linear response, you find a linear response. It's since this functional is quadratic, it's the problem becomes the solution of a big linear system. This is one possibility to do it. It's actually still implemented somewhere in Quantum ESPRESSO, because many years ago I used this approach to solve a specific problem, was Phonons in C60 or something like this, for which this kind of approach is more convenient than the one we are going to see, that is a self-consistent solution of self-consistent solution of smaller linear response. So what is the more traditional way to solve, to find the charge density, the linear response to perturbation? So the linear response to the perturbation in the linear charge response has to be written in terms of linear response of orbitals, of Kohn-Sham orbitals. So you don't compute directly this, but you compute those objects, or at least you search for those objects. The potential, the Kohn-Sham potential, has a bare term, and then has a screening term coming from the change in the charge density. Then you can use the perturbation theory to write down what those linear response of Kohn-Sham orbitals are. And if you use the perturbation theory, you find something like that. Now, this is written in a form that is not completely, not the typical way one writes the perturbation theory. Typically, one writes sum over conduction states. Yeah, you have a sum over conduction states, and the perturbing potential. Here a sum over conduction states that you can rewrite in this way as the green function. This is called the green function. 1 over energy minus the Kohn-Sham Hamiltonian is the green function of the system. Why there are these projectors over conduction states? Because the response appears by mixing, adding contribution from conduction state. It doesn't. If you mix states in the valence manifold, I'm assuming here for simplicity a non-magnetic insulator. If you mix states in the valence band manifold only, nothing changes. So it's just you are just doing a unitary transformation. So you don't get anything. What you get from a picture of conduction states. Now, this looks like a difficult problem, but actually it isn't that difficult. It can be recast under the form of a linear problem. So you have a linear problem that you have to solve. So here you have the perturbing potential, screen perturbing potential, the Kohn-Sham orbital, and linear response can be obtained by solving a linear problem. So it's a lot of linear problems instead of a big linear problem, but the small linear problems have to be self-consistent. So you have to ensure that the screen potential here is consistent with what you get here from the linear response of the charge density, which in turn comes from the linear response of the Kohn-Sham orbital. Okay, so come back in an hour.
Well, waiting for this problem. So the question in the middle. So what we do, we apply PC operator on the left and then on the right.
Well, maybe actually it's, I think it's redundant. It's redundant. The projector of our conduction state is used to get rid of contributions along on the valence band, on the valence manifold. Yes, I think here it's redundant because if you apply just here, should be sufficient. Well, this throws away all contributions along in the valence manifold. So from here, that doesn't make any contribution, new contribution in the valence manifold to appear. So it's actually redundant. Actually, what is strictly needed is to get rid of the projection of the linear response along the same function. So the linear response to psi v must be orthogonalized to the psi v. That's strictly needed. The rest is for notational convenience, basically. Just a reminder that only what comes from conduction state is important. The funny thing is that in spite of what I've been saying until now, that is that only conduction bands give contributions, give a contribution. Conduction bands are not needed. With this machinery, you never need conduction bands. In fact, the projector of a conduction band is the identity minus the projection over the valence states. And you solve, you have the Kohn-Sham Hamiltonian, so you solve these linear systems without resorting to any explicit sum of a conduction band, which is a good thing because, well, first of all, you would have to compute all conduction bands, which is something that, especially in a plane wave pseudo-potential framework, is something very expensive. Then you have an additional parameter for convergence, so how many bands you have to sum. And typically the answer is more than you think or more than you hope for. So it's good not to have to deal with the conduction bands explicitly. Notice that all you need in this machinery is a way to compute what you need from the point of view of functions that you can employ is to have access to this quantity, which looks terrible, but it's not. At least it can be even written down explicitly, analytically. It's a little bit, maybe a little bit complex, or computed numerically anyway. So for, let's say, ordinary type of exchange correlation functional GGA, all GGAs is not a problem. For more complex, more advanced functionals, it may be more of a problem. So, for instance, meta GGA has it's not implemented currently, for instance, in Quantum ESPRESSO for various reasons. One is that it is anyway very numerically unstable, as you all may have noticed yesterday. And also there are additional terms that appear. Another advantage of this procedure is that it can be easily generalized, easily used together with non-local pseudopotentials. Model pseudopotentials are non-local, typically non-local objects, but it's not a problem in this framework. At least for non-constant pseudopotential. For ultrasoft pseudopotential, things are a little bit more complex because there are additional terms. Linear response with ultrasoft pseudopotential can be done, but it's less convenient because there are more terms to be computed. And finally, what kind of perturbation can you deal with? Well, of course, you have a periodic cell, so you need something that doesn't break periodicity, apparently. So apparently you need periodic perturbations. But this is not true. You can deal with any perturbation that is monochromatic. So periodic times an exponential of this form. The reason being that the linear response to terms that are monochromatic is also monochromatic. So there are other wave vectors that are mixed with the current one, and so you can deal with each monochromatic perturbation separately. So you don't need supercells, unlike what you do in the so-called frozen phonon case, in which you may deal with perturbations like this, monochromatic perturbation, but if the wave vector is non-zero, then you have to expand the periodicity and to introduce suitable supercells. You don't need to work with supercells in linear response. Okay, let's come to the case of phonons. It's very easy it's a textbook problem to see what normal modes are in a molecule. You have to expand the energy up to second order and diagonalize the energy. You find that you have to solve this kind of specular problem in which this C matrix is the matrix of force constants, so-called MI epsilon. MI here are the masses of the nuclei. And this force constant matrix is given by second derivative of the energy with respect to nuclear positions. So these quantities are called interatomic force constants. And what happens in crystals? In crystals, you have to in crystals, the normal modes can also be are also block states, and so they are classified with by a wave vector. For traditionally, wave vector Q indicates phonon wave vectors, while K indicates block vectors for electrons. That's a tradition. I mean, it's nothing formal. We have always done it that way. That's why simply. So phonons are classified with wave vector Q, and what we have to solve is basically the transform of the previous equations for finite system for molecules. It's this is our equation, our secular equation that we have to solve to find the energies, which will depend upon energy, which will depend upon, also be dependent upon the wave vector. And this C tilde matrix is the Fourier transform of the force constant matrix. So in practice, what one is to do is to consider perturbation, monochromatic perturbation of this kind. So this U here is a displacement from the equilibrium. It plays the role of lambda in the first slides. There is no, I repeat that there is no explicit displacement. It's just a linear response to that displacement, the derivative with that displacement. What we compute is derivatives with respect to displacements. So this is the monochromatic perturbation these are the cell position, and these are atomic positions inside the cell, and this is the perturbation. And one can find that what we need to compute in the end is the second derivative of the energy with respect to this kind of perturbation. That's all we need to do. Which means that in order to fill the force constant matrix, we need 3 times number of atoms in the unit cell calculations, self-consistent calculation, self-consistent linear response calculations. Again, let me stress that we never need supercells. And let me notice that one may argue, why are you using static perturbation theory? In principle, you should use dynamic perturbation theory, time-dependent perturbation theory, because here you have a dynamic phenomenon. But in the spirit of adiabatic approximation, phonon frequencies are much smaller than typical electronic frequencies, and so we can use a static response. Okay, so this solves the problem of computing the force constant for one wave vector. You can diagonalize it and get the phonon modes at that wave vector. And that solves that problem. However, it is not very convenient. It's not a very convenient way to deal with an entire phonon spectrum, because well, you have to repeat the procedure for each wave vector, and that's expensive. But if you know instead, if you knew force constant in real space, you could compute force constant in reciprocal space for whatever wave vector you like. Now, how is this done? Well, you compute force constant on a grid of wave vectors, in a suitable grid. Then you make a Fourier transform back to real space, and you get force constant in real space. Of course, this works if force constants are short range, have a short range. And the shorter the range of force constant in real space is, the less wave vectors you need in reciprocal space, and vice versa. Typically, for a simple semiconductor, non-polar semiconductor like silicon and germanium, the example that I always show, the force constants are relatively short range, then you don't need more than a few calculations of a few wave vectors, relatively coarse grid of wave vectors to obtain excellent results, excellent convergence of the results. Still, it's a lot of calculations, and one has to resort to symmetry to reduce to the strict minimum the number of calculations, but one has also to avoid using a disproportionate amount of memory, because symmetry is used in sequential calculations. It's used to compute, to reduce the summation of our block vectors of our key points to the strict minimum, with the irreproducible sector, the irreproducible segment of the Riemann zone, so-called. So you just sum over a few key points and apply symmetry to the resulting charge density, and you get the correct result. This can be done also for linear response calculations, but you cannot use directly all symmetry as in the ground state calculations, because symmetry operations may send a wave vector into another wave vector. You should need to have to keep track of different wave vectors or response to different wave vectors in order to make the symmetrization. So there is a compromise that is done in which wave vectors, cube wave vectors, are computed only in the irreducible PUN segment, but you use the reduced symmetry, the so-called small group of the symmetry of the small group of cubes, called in group theory terms, so that you actually use more points in the summations that are needed to compute the charge density response than in the ground state calculation. This is a compromise between speed and memory, and explains why, if you look at the results of the linear response calculation, you will notice that the number of key points changes with the wave vector with the Phonon wave vector, because we use a different symmetry, typically lower symmetry for non-zero wave vectors. There are also other tricks to classify. There are 3N displacement, 3N linear response calculations, and these 3N linear response calculations are not performed as naively. One might naively imagine that is along the three Cartesian directions for each atom, but one finds the so-called irreproducible representations that transform into each other. These have a small dimension, 1, 2, 3, no more than that, and so you just need to symmetrize over 1, 2, 3 different linear response calculations. Okay, then if you do that, in the end you get some nice dispersion. These are all the results. There are much more interesting results for all kinds of phonons, but the story is not yet finished, because these are simple cases. In particular, in these simple semiconductors, what happens around gamma, that is Q equals 0, straightforward. You have 3 times degenerate frequency here. But if you consider slightly more complex semiconductors with a zinc blend structure, in which the 2 atoms from the 2 sublattices are not the same, so gallium arsenide and aluminum arsenide, the object like this, and you will notice that there is a splitting. It's called the LOTO splitting, longitudinal optical transverse optical splitting. So longitudinal and transverse with respect to what? With respect to the direction along which you go to zero. So it's a little bit tricky because what happens at the Q equals zero, it's not easy to be connected to what happens when you go towards Q equals zero. And also I'm not taking into account the fact that a correct electrodynamic treatment would lead to the disappearance at Q equals zero, exactly zero, of the longitudinal optical, transverse optical splitting. But if you look at what happens for a sufficiently small Q, but not exactly zero, that's the situation. You have the modes, the longitudinal, one mode that has a higher energy with respect to the transverse mode. This is something that is very important because zone center phonons, so Q equals zero phonons, are what are typically observed with infrared spectroscopy. Now, how can we deal with this LOTO splitting in linear response calculation? It's possible, it's slightly tricky, but not even that much once you have figured out how it works. Actually, the theory is known since many years ago, since a big book written by Born and Wang in the 50s, so many years ago. They look at the behavior, so-called long wavelength theory, the behavior for wave vector tending to zero, what happens with that limit. The problem is, what is the problem? Why don't we just do the calculation at Q equals zero and that's it? Because the longitudinal, the LOTO splitting is due to the appearance of a macroscopic electric field. Macroscopic electric fields in solid state are difficult to deal with because, as Nicola Mazzari mentioned yesterday, they are not consistent with periodic boundary conditions. So the electric field, the homogeneous electric field, has a potential that goes like R. Electric field scalar product is R. Something that is not known about in the periodic system. Actually, there are ways to define the R operator in such a way that is consistent with periodic boundary conditions. You can read papers by Raffaele Resta, who is a great expert of this kind of problems. One can deal with the modern theory of polarizability with this system, but even in a linear response approach, one can deal in a simpler way, straightforward way, with the electric fields anyway. So what happens is finally that you can write down in phenomenological form of the energy in which you have the energy from phonons, this term here, from atomic displacement, which is given by the usual quadratic form, in which here you have the force constant that you compute in whatever way you can. Then you add, let's say that you add manually a macroscopic electric field. So this is valid in the limit of Q equals zero. So you have the electric energy term, which is also quadratic in the energy, in the electric field. And you have the term that connects the two phenomena, the macroscopic electric field and and the displacement of atoms and the phonons. Now you can use this phenomenological expression, for instance, to find the nuclear contribution to the dielectric constant. This dielectric constant here, dielectric tensor, actually is a tensor in principle. These are also tensors. The Born effective charges are also tensors, and they are not even symmetric tensor. This term here, I've lost track of what I wanted to say. This is the electronic part only of the dielectric tensor. So there is also a contribution from nuclei, and it can be obtained quite easily by finding the displacement that minimize this quantity, this energy, given an external electric field. Actually, we are interested in the opposite. So given atomic displacement, what are the macroscopic electric field, and with some electrostatic, we can find that the so-called electrical induction, the electric field, so-called, the one that has zero divergence and this form, so the electric field plus the polarization that has a term, electronic term, and an ionic term, which depends upon the Born effective charges. And we know that this is in the limit Q tending to zero, it has zero divergence always, and the limit Q tending to zero, this means that it has to be orthogonal to Q, which means that the curl of the electric field has to be zero, which means that the electric field can only be longitudinal, so directed along the Q vector. That's the only possibility to have a macroscopic electric field, so it has to be longitudinal. And putting all things together, one even finds what's the value of the macroscopic electric field. And putting it back into the previous expression, one finds that the energy as a function of atomic displacement, including macroscopic electric field generated by atomic displacement, has the usual quadratic form, the expected quadratic form, in which you have an analytical term, so-called analytical term. So the force constant you compute from the calculation, basically. You compute from linear response or from whatever. You compute by ignoring macroscopic electric fields, let's put it that way, plus the term that comes is non-analytic, that depends upon the direction of Q, of the wave vector, and that has this form, and that gives rise to the LOTO splitting. How much time do I have? I haven't noticed when I...
10 minutes. Yeah, 8 minutes.
Okay, so finally, so we need to compute, if we manage to compute in addition to the force constant, which we know how to compute, we just ignoring the macroscopic electric field. If we compute the dielectric charges, the dielectric tensor, and the effective charges, then we are done. Now, if one looks at the definition of those two quantities, one finds that both are actually derivatives of the energy, or related to derivatives of the energy. Second derivative of the energy. So the effective charges are the polarization induced by lattice distortion, or the force induced by an external field. The electric tensor instead of polarization induced by the electric field. Now, so this means that they can be computed in using linear response as long as one finds a way to manage with such an object, which with a potential. Sorry, here the notation is not consistent with the previous one. So let's say, oops. Let's say this should be the linear response of the potential. No, not the linear response. It should be the derivative of v with respect to. Okay, let's assume that this is just a first order variation of that we apply with an electric field. Okay, this is ill-defined in a crystal, but if you look at what you actually need, we need only matrix elements. Implicitly, we need only matrix elements of this object between valence and conduction states. What is ill-defined is matrix element on the same Kohn-Sham orbital. So psi v r psi v ill-defined, but those quantities can be defined in a correct way by resorting to this trick by introducing the commutator of the Hamiltonian of the Kohn-Sham Hamiltonian with R. The commutator of the Kohn-Sham Hamiltonian with R is a simple object. It's basically the momentum, which is well defined. The momentum plus, since we may have in the Hamiltonian and the Kohn-Sham Hamiltonian, we have a non-local potential. The local part of the potential doesn't give any contribution, but the non-local potential here gives a contribution, which again, anyway, written explicitly. It's also something that you can compute. It's a little bit boring, but it's simple and it's well defined. So this commutator of the Hamiltonian with R is a well-defined object that you can put it here and it works. It has no problem of ill definition. And if you notice here, there is a sum. Actually, we are summing over, making perturbation sums over conduction states, which means that we can resort to the usual trick of transforming into Green's function times something that is solving a linear system. So we just have to solve a linear system to find this object here, which can be defined in terms of this known quantity, which can be computed. Now, so we have the possibility to compute the response to an external electric field without any special problem. And finally, we just have to find the polarization induced by an atomic displacement, which also looks horrible because if you write it explicitly in this way, this looks like something that is very ill-defined for the usual reason. But again, if you rewrite this via Kohn-Sham orbitals, then you realize that with a similar trick, tricks are similar to those that I've shown before, in the slide before, this can be written in a way that is consistent with perturbation, with periodic boundary conditions. Notice that here you can use the fact that mixed derivatives are invariant with respect to exchange of derivative of what you derive. And so you can compute effective charge both as a polarization induced when atomic displacement, or more easily as the force acting and produced by an external electric field. Okay, and the same with the same ingredients, so the same ingredients that are used in the calculation of effective charges can be used directly to compute the electric tensor in a similar way. Of course, this is not the only way to compute those quantities. There is also the modern theory of polarizability, but this is, if you are dealing with phonons, this is a very convenient way to work. There's a final problem, that is the procedure that I have described before to extract atomic force constant in real space from Fourier transforms works if and only if the atomic force constants are have a short range. Unfortunately, if you just take the Fourier transform and transform it back into real space, you don't know of the force constants for a material, for a polar material, and almost all materials are polar. I mean, there are just a few simple semiconductors that aren't. If you do that directly, you won't get anything sensible because of the non-analyticity of it is contained in these Fourier components. What has to be done is to subtract out a term that contains the non-analyticity at Q equals 0. Then what is left is analytic and short range. Then you add it when you compute again the force constant at the generic wave vector. You have to add back what you have subtracted before. But it is a term that is easy to add back. Actually, I'm neglecting something that should be taken into account. Actually, so there is another term that may give rise to some non-analyticity in the Q equals 0 limit. It's a photopolar term, dynamic photopolar term. It's explained in this recent paper by Roy and Stengel, and it's not yet included in Quantum ESPRESSO, but apparently it's coming soon. Okay, so phonons for polar materials, and of course there are many more examples of phonons that have been computed during the years. I'm not going to make a review of phonon calculation, but let's say that a linear response allows to compute phonon dispersion for a large variety of materials. As long as your DFT description is good, your phonons will be good as well. And calculation may be a little bit expensive, but not that much. There are a few other things that can be directly computed with linear response. One is the typical one is the infrared intensity, which is related to the polarization induced by a phonon mode. It's straightforward. Or thermal properties, you can compute in a quasi-harmonic approximation. So you use harmonic phonons, and then you take into account at least partly the anharmonicity by considering how it changes with volume. That's the easiest way to take into account some anharmonicity into the calculation, in particular into thermal properties. Finally, a side product of linear response calculations that is very useful, and Samuel after me will show what you can do with that, is the response of the potential, because it's the basic ingredient to compute electron-phonon interaction coefficients, which means superconductivity, which means transport, which means a lot of interesting stuff. So this is something that comes out, is derivative of the potential with respect of the self-consistent potential with respect to the Phonon mode is something that comes out from the calculation naturally. You just store on disk and then you can compute those matrix elements and do whatever you like with that. I think it's all I wanted to say. Sorry for being a little bit late.
No questions?
Thank you very much for the talk. You mentioned somewhere we can reduce the number of Phonons correlations we perform to switching. You mentioned the compromise between speed and accuracy. But where is the compromise in accuracy?
No, the compromise is not in accuracy, but in time and memory. That's a compromise. That is, if you may reduce the time and use the full symmetry you have, but then you have to keep track of a bunch of linear response calculation at the same time, because you are symmetrizing objects that are done in another, that are available in another calculation. So you have to make a lot of calculations together, and that's impractical.
Yeah, thank you. I misheard it.
Lauren?
So thank you very much for the talk. I have a question about the future. So I don't know if you aware about this automatic differentiation method that allows to compute automatically gradients from the code, and you have a perspective this can somehow be used to compute also Phonons in more complex functions.
I've heard about these automatic differentiation methods. Maybe I'm too old to understand them. And my impression is that they are not suitable for such a rather complex calculation. So, well, in principle, you might, but even without automatic differentiation, there's already a sort of automatic differentiation that is Phonon. You may like it or not, but finally, Phonon does more or less that, by displacing objects, actually displacing, not computing the linear response, but actually displacing. Maybe it could work, this automatic differentiation, maybe it could work, but not taking advantage of anything that we know about the system, symmetry and many other features of our system that we take into account, we are aware of. I mean, the spirit of times is in things done automatically, but sometimes it may take a disproportionate amount of time to do just blindly, not using what you know about your system, using blindly automatic techniques may lead to a disproportionate amount of computation. Or maybe I'm wrong. I don't know.
Another question?
I forgot to sort it. It was follow up on that. So my point was we look at so my point is about causing Phonons. So is there a systematic way to understand, let's say, what the calculation is faster? So of course, if you need to do you going to zero limit, let's say the Phonons around gamma, it's problematic because you need gigantic supersets, let's say. But
I don't know, I would like to have a table, let's say a benchmark on how is it faster with linear response theory with respect to that than Hubbard and Koopmans. Is that something like that? Does it exist?
I don't know if somebody has ever done that kind of comparison. My opinion is that the reason that keeps frozen phonon alive is that with frozen phonon you can do calculation that in linear response are really hard to implement. Not that it can be linear response is faster. I'm quite sure that it's always faster, but almost always maybe.
I agree.
Hmm?
I agree.
But there are some calculations that with linear response are difficult to do because well, they have to be implemented, and yeah, this is a mess sometimes, depending upon. For instance, DFT plus U phonons exist. They can be computed, but it's
Yeah, I can comment. So, in the simple system, like non-conservative potential, etc., what I mean, what I call from 30 years ago, let's say, the calculation of a full phonon dispersion is linear in the number of Q vectors that you include, which means the linear in the dimension of the cell that you want to. You would use in the corresponding frozen phonon calculation. So then there is an advantage of linear scaling with respect to a cubic scaling. So in this sense, what cubic or even
It's more.
even more. You have also the different displacement. So in this sense, it is easier. It is faster if you have the code. The problem is that having the code for LDA plus 2 took a couple of 2-3 years. And so, I mean, it's human time versus computer time often. And yeah, I think this is the question.
No, then I have a follow-up on this because I think it's very important. So the problem is that when you put an implementation like this there, let's say, so two things I have to do the forms, properly here plus U, because also the work of Matteo and in response DSP plus U, then they did the ultrasound intervention. So the point is that now that I do the calculation in Quantum ESPRESSO, I don't see the difficulty, you see. So because I just I don't even do anything. I just I just put the DFT plus thing, and then I ask to do the forms, and it's so seamless. It's all the years, let's say. It almost seems that that they can use all these techniques, but then the research that did all the effort doesn't get credit, don't get credit enough. So this is my opinion, because indeed, so indeed, I think that actually for this, so since now implementation become incredibly difficult, because this is indeed one example. I don't know, maybe another way of citing using this stuff indeed. So it's 3 years implementation, and then what do you get? So this is the problem.
You get nice phonons.
Yes, everyone gets nice phonons. You don't get any credit. I don't know. So yeah.
That's more of a sociological problem. I agree. It's,
no, because
sometimes the effort is not worth the result.
Yeah, no, I'm just thinking about can you just find different for example, compute the dynamic, the own charge in the electronic dielectric constant, you still need linear response. Actually, but there are other kind of.
Well, yes, we need. Well, for the dynamical charges, you can use Berry phase. For the electric tensor, well, you can do one linear response calculation. It's not expensive anyway. Or you can you can use experimental data. I mean, it's 9 numbers, 6 numbers, because it's
So
thematic.
again, to comment on this, elastic constant in principle is are also something that we could do with linear
Yes,
response.
yeah. Haven't mentioned that there are many
And,
other calculations that can be done with linear response, but
I looked into the formula, and I decided we will never do that because
you don't want
there
to
are
do
in
that.
principle only 6 different perturbations that we can do with the. I mean, the problem of the phonon, let's say, advantage for the phonon is that you also have a few vector dependence, and so in order to describe that, we need a big set. For the elastic constant is again a Q going to 0 limit, which you can do with clever stuff, but then in the end you have to deal with a few, I don't know, 6 independent perturbation, and to do it by numerical differentiation is so much easier than implementing the equations. So I never did it.
So maybe I don't know, Lorenzo. On Friday we present AIDA hydronic workflow. So maybe you want to comment about the relation of formulas.
Then also the other possibility of doing it with finite electric fields. So yeah, there was this huge problem of how we describe the allostotic. I mean, I will show you the floor.
Displacing the atoms.
Well, I mean, at least if you do the figures obtain simultaneously both the electric tensor and the positive charges. And also,
If you manage to convert the calculation.
but I managed to tweak the record.
For the electric field, you just need the 3 calculations and get the effective charges on every point. That's why many years ago I made a square now.
Yeah, no, the problem is not that it's in principle the one after the other. The problem is I think implemented now that we are looking big and it's if the cell is a little bit big, it becomes very expensive.
The issue is more, I mean, I think one has to separate what you can't do, and the issue is doing some of these things with the, other functions, with the hybrids and so on. If you can't do otherwise, and then you have to do what VGA calculations. I mean, it's always for me to separate the response.
Other questions?
Yeah, just wanted to make a comment about the difficulty of implementation of Phonons, for example, in GG, as you. The difficulty was more from with the infrastructure potential, I would say, because if non-conserving would be much faster, and also it's faster to debug. With Microsoft, we had a lot of little subtleties, little bugs, very nasty bugs, and then this took time in terms of finding the bugs, and also the format is much larger. So that was I wanted to add this. It's really
Thank you. Yeah, if I may ask the last question. So we were arguing quite a lot for chromium triodide. So let me just explain. If you take chromium triodide as a bulk, so it's let's say 2D material. So it's very ferromagnetic insulator. So you have like 1.2 eV band gap. So if you look at the lowest conduction bands, you have spin up and spin down, which are more or less aligned at 1 eV above the home. So PBSO is described systematically, but then if you apply to SU, what you see is that this low conduction bands and spin up and spin down, they are shifted, which contradicts two experiments. So we're wondering if you are messing up conduction bands, are forces, stresses, phonons affected, or they are not? Because we have this projector PC equal 1 minus PD. So it's about to rearrange bands in the empty band manifold, but still use 1 minus PV. So what is your thought on that?
Well, by the way, there is an extension of linear response to metallic systems. They found it many years ago. But I don't think that the problem is in the projector, but probably that if you have a functional that doesn't function, doesn't describe correctly the system.
But even if I artificially shoot by hand, empty bands somehow randomly rotated. So do you expect Phonons force and pressure to be sensitive to this, or they're like ignorant to how you move bands empty bands because they're empty? What we care about now, occupied bands. While in perturbation theory, you write the response wave function as sum of empty bands. So it's matrix elements occupied and empty.
Also, something that I haven't mentioned is that this machinery is actually, the response is actually ground state property. So even if conduction bands seem to appear in the formalism, actually it's a ground state property. So it's not, it doesn't depend upon excited states.
So this means that it should not be affected.
If not, yes.
No, but if you use a DFT plus 2 functional, I think it's much more complex than that. So you're talking about DFT plus 2, it has the occupation matrix of the unoccupied manifold counts. So it is a grounded property if you use DFT. If you use DFT plus 2, it is fine.
Maybe let's see.
Yeah.
I think you guys. Yeah, food for thought. Okay, in the interest of time, let's thank again our